Jai Hind, my dear students. Myself Dr. Neelesh Kumar Gupta. I am working as a professor at Ajay Kumar Garg Engineering College, Ghaziabad, in the Department of Electronics and Communication Engineering. So, in this lecture series of subject Digital Signal Processing, I will give today my lecture number 2. Okay, that title will be Impulse Invariant Transformation Method. Its AKTU code is KEC 503. So, today we will see about the Impulse Invariant Transformation Method. This is the method for IIR filter designing. If you want to design IIR filter, then you can prefer this Impulse Invariant Transformation method. It's very popular method. Okay. Generally in your examination, always question will be asked from this method. Okay. So, that we will see here. Okay. So, here infinite impulse response digital filter design. So, this is my main title. Okay. IIR digital filter design. So, in this, actually this is your unit number 2 of KEC 503. So, these are the titles. Okay. Under unit number 2 you will study. Okay. For the course of digital signal processing. So, here introduction to filters. Okay. Filters, it means what is the meaning of filter, how you classify the filter. Next you come on digital filter and how the digital filters are different from the our analog filter. Then some designing methods. Okay. So, some designing method, impulse invariant method, bilinear transformation method, then all pole analog filters method, under which you will see Butterworth and Chebyshev methods. Then designing of digital Butterworth and Chebyshev filter, how you design using the Butterworth and digital filter designing, then frequency transformations and their limitation of the given methods, that you will see, you will study in this unit number 2 of digital signal processing subject. Its AKTU code is KEC 503. So, let us see here. Now, IR filter designing method. So, generally IR filter designing methods is simple, because you have to convert, you have to map your S domain or S plane into the Z plane. You have to convert, you have to map your analog filter transfer function into the digital filter transfer function. So, mainly 3 methods are there: approximation of derivative, impulse invariant transformation and bilinear transformation. So, in this lecture I will tell you about the impulse invariant transformation method, by which you can design IIR digital filter. Okay. So, in IIR filter design, so these 3 methods that I told you, in these 3 methods generally what we will do, that I will tell you by this PPT. So, objective of digital filter design is to develop a transfer function h of z meeting the frequency response specification given in the problem. Okay. So, you have to develop, you have to convert your specification into h of z, this. So, in digital filter designing IIR, you have to prepare, you have to finalize h of z. H of z means what? It is transfer function or system function of digital IIR filter. So, then standard approach. What will be the standard approach? What is the basic concept behind this? So that you can convert, you can prepare your h of z. Okay. So, convert the digital filter into the analog prototype low pass specification, determine the analog low pass filter h of s. Generally some specifications are given to you. So, you should know the h of s. Sometimes you have to derive h of s, then you have to convert this h of s into h z. Okay. So, h of s means the transfer function of analog digital filter. And you have to convert, you have to map, you have to transform this h of s into h of z. That we will do in this impulse invariant method. Sometimes in Butterworth and Chebyshev, one step is also you need. Okay, what? That from filter specifications, some filter characteristics, you have to prepare first Hs. Then you have to convert this Hs into Hz by using impulse invariant or bilinear transformation method. Next, let us see if analog transfer function, A means analog. Okay. So, here A subscript shows the analog domain. So, Hs is equal to Ps upon Ds, okay, where subscript A indicates the analog domain. Okay. So, you have to convert this Hs into Hz. Simple task. What? We have to convert this Hs that is given in the problem generally into the capital H of Z. That you have to keep in your mind. So, basic idea behind the conversion of Hs into Hz is to apply the mapping from S domain to Z domain. Because if you have to convert Hs into H of Z, so what you are doing? You are going transforming, converting, mapping from S domain to Z domain in such a way that our essential property of the analog frequency response are preserved. It means input output does not change. If you are mapping, you are transforming Hs into Hz, so then same characteristics available in analog filters will be in digital filter, design digital filter. Thus, mapping function should be such that the imaginary axis in S plane be mapped into unit circle of Z plane. Okay. So, because we know the S plane, what is the S plane? This is our S plane, this is our sigma, this is our j ohm, real part, imaginary part, this is our S plane. For Z plane, what you do? For Z plane, you have to draw unit circle. So, you are mapping or you have to map this S plane into the Z plane, and generally you have to achieve stable analog transfer function into the stable digital transfer function. So, H of S that is already stable, and you have to map this H of S that is already stable into the stable H of Z. That is our objective. So, generally what we are doing? We have to convert here S plane into the Z plane. S domain quantity are into the Z domain quantity. Now, we come on our main title, that is impulse invariant method. Earlier in some previous PPTs, I am trying to tell you about the basics of designing of digital filter. Basically what we will do. So, first method, that is our title of this lecture, that is impulse invariant method, I will tell you. Okay. So, in impulse invariant method, in the diagram it is clear, this is many to one transformation, many to one. It means at first you have to understand, you have to map your S plane into the Z plane. So, S plane quantity you have to map into the Z plane quantity, that you have to understand. Then stable H of S you have to map into the stable H of Z. Okay. So, many to one transformation, I am writing here many to one. What is the meaning of this? Many to one means, so if I am considering here the stable some poles, distinct poles in stable region, if I want to map these stable distinct pole into the Z plane. So, these all will be collected, will be available, will be mapped into the same point. That is why I am writing many to one transform. So, many to one mapping. So, impulse invariant method is based upon the many to one mapping. It means the distinct poles available in S plane of analog filter will be mapped into the single point in Z plane of unit circle. Okay. So, due to this some limitations also will be there, that I will tell you after this method. Now, these are the designing steps. How you design, how you convert your HS into HZ using the impulse invariant method, that I will tell you. So, at first H of S is given to you. H of S is what? H of S is analog transfer filter transfer function. So, at first what you have to do? So, if H of S is given to you, so in the first step, this is the first step, you have to take inverse Laplace transform of H of S. If you take the inverse Laplace transform of H of S, then you will get H of T. So, this is our first step. What? H of S is given to you, and what you have to do? You have to map here this HS into HZ. So, at first you have to take its inverse Laplace transform, then you will get H of T. This is our impulse response in discrete domain, in analog domain. Sorry. Now, because H of S, this is our what? The transfer function of analog filter, and this is our transfer function of what? Digital filter. Okay. So, H of S is given to you. At first, in the first step, you have to take its inverse Laplace transform. Then you will get impulse response in analog domain. After that, you need sampling here. This method name is impulse invariant method. It means uniform sampling you have to do here. You have to prepare here equivalent discrete signal related with analog signal. So, you have to prepare, you have to do sampling here, and you have to create its equivalent signal here. So, here you are doing the uniform sampling. If simply if we understand, so simply you can understand, you have to put small t is equal to nt, then you will get h of nt. Then this is our second step. Okay, what you have to do? Uniform sampling. It means you have to convert its equivalent signal in discrete domain. Okay. So, generally in mathematically if we see, so h of nt means you have to put t is equal to nt, then you will get simple h of nt, and this h of nt is equal to h of n. This is what? This is impulse response in discrete domain or impulse response sequence. So, this is our second step. First step was what? You have to take inverse Laplace transform for getting the small h of t. After that, you are doing the some sort of sampling, uniform sampling, and you are converting this h of t into h of n. And t is what? T is our sampling time interval. Okay, that is t is equal to 1 upon fs. Fs means sampling frequency. In the last step, now you are getting h of n. What your motive? Your motive is what? Hs you have to convert into h of z. How you will get the h of z from h of n? Taking the z term. This is our third step. Now what will happen? You are converting your hs into hz from these three basic steps. So, by using these three basic steps, you can convert, you can map, you can transform your hs into hz using the impulse invariant transformation method. I think it will be okay to everybody. So there are three formulas in this, basic three formulas in this method. First for linear factors, second for cosine form, third for the sine form. Okay. So that all formulas we can prove applying these three simple steps. First, you have to take inverse Laplace transform. Second, you have to make small h of t equivalent to small h of l by using the sampling, uniform sampling process. And the last step, you have to take its Z transform. Then you can convert, you can transform, you can map your Hs into Hz. So in the first formula, if I am supposing here, if our analog filter Hs is equal to summation of I to m ai upon s minus pi, I am supposing here this is our Hs. So by using impulse invariant, you have to convert this Hs into Hz. So what you have to keep in your mind, three steps here. In first step, what you have to take, what you can do, you have to take its Laplace inverse transform. So if you take the impulse inverse Laplace transform of Hs, okay, so it will be Hat is equal to summation I 1 to m ai e to the power pit. We know in Laplace 1 upon s minus a. So its Laplace will be e to the power at. Similarly here e to the power pit. Now uat I am associating here. What? Why? Actually this is what we are discussing, IIR digital filter. IIR means what? Infinite impulse response digital filter. It means the such type of digital filter whose impulse response lies for infinite duration. So u of n or u of t is such type of function, unit step function, UAT. UAT is continuous unit step function, that's value will be 1 from 0 to infinity. If I am associating this one, so it will be applicable in IIR. That's why I am associating u of at. Okay. So the first step I have completed here. What? I am taking inverse Laplace transform of h of s, Hs, that is earlier I defined here. So I am getting h small h of at. In second step, what you have to do? It's uniform sampling, or you have to convert this Hat corresponding to Hn. Simply what I told you? I told you have to replace simply small t is equal to what? Small n into capital T. So it will be Hn is equal to Ha n t. So ai e to the power pi small n t ua n t. So second step I have completed here. In third step, in final step, what you have to take its Z transform. Okay. So if you take the Z transform, you know the formula of Z transform, h of z is equal to summation from n 0 to infinite small h of n into z to the power minus. So I am putting the value here in the formula. Okay. Why I am taking 0 to infinity? Because we are working for IIR. In IIR, if u of n, u of t I am associating, so obviously it will go from 0 to infinite, because u of t or unit step function gives 0 value for less than n 0. So if you take the Z transform for this, then applying the some formulas and calculation, you will get h of z is equal to this one. Okay. Summation from I 1 to m ai upon 1 minus e to the power pit into z to the power minus. So I am converting h of s into the h of z by using impulse invariant transformation method. So if you compare, then you will find what? I am preparing equivalent of 1 upon s minus pi into this form, 1 upon 1 minus e to the power pit z to the power minus. So, in this way we can convert, we can transform, we can map h of s, or we can also write HAS into HZ. So, you can transform, you can map your HS into HZ by using these simple 3 methods. Okay. So, now you can also analyze something from the equation z is equal to e to the power st. If you put z, it means r into e to the power j omega. Z means what? It is in digital domain. S means it is in analog domain. So, e to the power sigma t into e to the power j ohm t. Now, if I compare the terms this and this and this and this, so we will get this term. Okay. So, some analog and digital poles you can compare here from these expressions. Okay. So, one formula I am telling you here, and also I told you how you prove this formula. Okay, how you prove these formula by using 3 basic steps. Similarly, 2 another formulas also are there in this method. Second is our what? S plus A upon S plus A whole square plus B square. It will be equivalent to, it will be equivalently mapped to this formula. In third, B upon S plus A whole square plus B square, that is should be mapped, will be mapped into this formula. This is in cosine term, okay, and this is in sine term. If you see these formulas, so these are exactly very common terms are there in these formulas, and you can remember easily these formulas. So, in this way these 3 basic formulas are there by which you can convert your HS into HZ, because in the examination either these formulas you have to prove, or any expression H of S is given to you and you have to think there ki which formula will be suitable for that expression, and directly you can put the its equivalent this and this, and so that you can prepare the H of Z from given HS. Now, this some examples also I am taking in this lecture. So, in example number 1, if H of S is equal to 2 upon H square plus 3S plus 2. Now, you have to determine the H of Z for t is equal to 1 second and 0.1 second. So, H of S is equal to 2 upon H square plus 3S plus 2. If you see this, so no formula is applicable directly for this expression. So, at first you have to simplify this. How you simplify any expression? By using either factorization or partial fraction. So, you have to take partial fraction here. Okay. So, at first see that the factorization is possible or not. So, if you see here, so you will get 2 upon S plus 1 into S plus 2. Now, further simplification you have to do partial fraction for this. Okay. So, how we will take? It will be A upon S plus 1 plus B upon S plus 2. Now, using the partial fraction method, you can calculate the value of A and B and put into the equation. So, if you do the partial fraction, okay, for this, then you will get A is equal to 2 and B is equal to minus 2. So, for this subject, always remember that your mathematics should be good, your calculation ability, that is very, very important. So, by putting the value here using the partial fraction, because you have to split in partial fraction in this way, again I am writing this one. Now, you can calculate by using partial fraction method A and B value. So, A you will get 2 and B you will get minus 2. Then H of S is equal to 2 upon S plus 1 and minus 2 upon S plus 2. Okay. So this is our simplified HS. Now you have to convert this HS into HZ. So you will see here what you will see here. You will see here this is for linear factor. So directly you can put the formula here. Okay. So for linear 1 upon S minus Pi, you have to convert into the 1 upon 1 minus e to the power Pit Z minus 1. So 1 upon S minus 2 is there. So it will be converted into the 1 upon 1 minus Pi means 2 T Z minus 1. If 1 upon S plus 2 is there, then it can be converted into the 1 upon 1 minus, this is plus 2. So e to the power minus ka 2t Z minus 1. So directly you can put this formula and you will get the answer. So here what? Directly you can put the formula here. You will get what? This will be, it will be converted into the 2 common. You can take the common 2. So first one will be 1 upon 1. What it will be there? 1 minus e to the power minus t Z minus 1 and minus 1 upon 1 minus e to the power minus 2t Z minus 1. Now you can take the LCM and solving this factor, you will get h of z is equal to this one. After the putting the value of t is equal to 1 second. So t is given in the question, you can put the value of t at the last and you will get the answer in this. So you have to use these three formulas in terms of linear factors, some cosine form and sine form. And you can map, you can convert, you can transform your HS into the HZ. Okay. Now another example we can see here. Determine HZ using the impulse memory technique for analog transfer system function for this. H of S is given in this type now. Now what I told you in last PPTs, these three formulas, these three basic formulas are there that can be proved by three basic steps. That also I told in my last PPTs. Now these three formulas you have and you have to apply these three formulas into given H's and check whether which formula is suitable for that expression and you can achieve your HZ that you want to achieve here. So in this question you have to determine H of Z if H of S is given to you using the impulse invariant technique. So at first you have to solve this one because directly if you see, so no formula I can put directly here. Okay, one linear factor is there, but some quadratic equation also will be there. So what I do? So I am using the partial fraction. So a upon this is the linear and this is quadratic equation. So what in partial fraction a2s plus a3 upon s square plus 0.5s plus 2. Now you solve this by comparing both the sides. Then you have to do what? For calculating the value of a1, a2 and a3. So after solving you will get a1 is equal to 1 by 2, a2 is equal to minus 1 by 2 and a3 is equal to 0. So partial fraction you should know very well because these will be beneficial for you for realization, for designing and another things in digital signal processing subject. So if you put the value of a1, a2, a3 here, you will get HS is equal to this because a3 kya tha? What was a3? a3 is 0. So it will be 0.5 upon s plus 0.5 minus 0.5s upon s square plus 0.5s plus 2. Now this term, this is the linear factor term, so easily you can put the value, okay, converting value, but this it is not like another terms, okay. So you have to make this, okay. So if you take the 0.5 common here, so it will be s upon s plus s square plus this. So what you can prepare here, you know s plus a upon s plus a whole square plus b square. So this equation, this will be like a this type of equation. So S plus A. So at first you have to prepare this in whole square form. So in whole square form it will be S plus 0.25 whole square plus 1.3911 whole square. Now in the numerator you need S plus 0.25. So you have to add plus 0.25 and minus 0.25. Two terms will be there. So this term like this one simply here. Now this term if you see here after the solving this, because it S is not there, so it will be in terms of B upon S plus A whole square plus B square. Okay. So it is like this. Now used all three formulas here directly and you will you can calculate the H of Z. This is for linear factor, this is for cosine, this is for sine. Now you are putting the value directly here. At the last you have to put t is equal to 1 second. And now this is your H of Z. Further you can also simplify this and you can calculate H of Z into the single expression, single term in numerator and denominator. Okay. And always you have to calculate the angle, okay, in radian. Okay, this you have to keep in your mind, not in degree. Now next question, convert the analog filter into digital system function is this. So this is simple. This is like किसकी तरह है ये? What? It is like second formula, that is cosine base. What? S plus A upon S plus A whole square plus B square. So here B is equal to 3. If you compare this one, so directly you can put the formula of cosine and you will take the H of Z. After putting the t is equal to 1 second, you will get the H of Z. So directly you can put. Okay. So three basic steps are there in impulse invariant method. By those basic steps you can design any type of HS into HZ. But mostly we study three formulas. First for linear factor, second in cosine term, third in sine term. You can prove by using those three steps, basic steps. And now if H of S is given to you, you have to prepare, you have to make this HS into HZ using those three formulas. Now for the next question, HS is equal to 1 upon S plus 1 into S plus 2. You have to determine HZ using the impulse invariant. What you have to do? Again this is 1 upon S, this is the linear factor, but you have to solve this at first. After that you have to take the H of Z. So at first what you do? You do the its partial fraction for getting the value of this A1 and A2. If you solve then A1 A2 you will get H of S is equal to this one. Now you know H of Z correspondingly these are the what? These are the linear factors both. So directly you can put the this into the Z form by first formula for linear factor. So it will be this 1 upon 1 minus e to the power minus 3 Z inverse minus 1 upon 1 minus e to the power minus 2t Z inverse. Now you take the LCM of these two and solve this, okay, and at the last you have to put t is equal to 1 second. Generally t is given in the question in impulse invariant method. If it is not given or any other conditions are not given, then you can assume t is equal to 1 second. Okay. Remember this point. Okay. Now advantages. So this is a very simple method. Only you have to remember three formulas and three basic steps by which those three formulas can be derived. Only you have to apply into this given HS, but your mathematical calculation ability should be good, then you can do. So it produce the stable design. Now analog frequency, digital frequency are linear related. You know ohm is equal to omega upon t in this method. Ohm is what? This is analog filter frequency and omega is digital filter frequency. digital filter frequency. Okay. So the relationship between the ohm and omega is linear here. Limitation. So what I told you initially in this lecture, this method is based upon the many into one transformation. So many into one transformation, due to this, the aliasing will be there. Okay. So limitation what? Impulse method can only be used for realize the in designing the low pass filter and some limited class of band pass filter. It cannot be designed for high pass or certain band reject filter. Why? Because due to the many to one mapping. Because distinct poles, if these map into the single point in Z plane, so all will be overlapping in each other. If overlapping in each other, then obviously aliasing will be there. That will be highly undesirable. Okay, this in many into one. If the distinct poles you are taking into the S plane, if these are mapped into the single point in Z plane, so obviously aliasing will be there. So this is our limitation. So how you remove this? Because aliasing, why aliasing will be there? Because f of s less than twice fm. So to avoid the aliasing, what you can do? Always you should take the fs greater than twice of fm. It means frequency is high. So you have to choose, you have to select what? Small sampling time. Okay. If frequency is high, the time will be less. So the value of sampling time can be chosen very small to mitigate the effect of aliasing or another transform such as bilinear transform that removes this many to one mapping and based upon the one to one mapping. That is our bilinear transformation. So to overcome the limitation of mapping from S plane to Z plane in impulse inversion method, we need another transformation method that is called bilinear transformation method. So it will be based upon one to one mapping, not many to one, one to one mapping. Okay. So that's all about the impulse invariant method. So that's from my side. Okay. I hope all the terminology, all the terms that I explained in this lecture, that will be clear to you. Okay. So thank you very much.